Hello everyone, welcome to Vedanta JEE English channel. Okay, we are left with some portion of semiconductors, right? We will be completing it today along with the PYQs. So what I have done in the previous class, whatever the PYQs which are related to that, whatever the theory I have done, I have taken them up. Now majority of questions are going to be on Zener diode and logic gates. So I have picked all the PYQs of 2024, also of 2023 if needed. I have taken some 2023 PYQs also, so that your conceptual understanding is going to be better. Majority of times from semiconductors, logic gates is the place where a lot of questions are going to come. After that, Zener diode, and very few questions are going to be from the portion which I have done in the previous class, right? If you people confirm that, if you are able to hear me and if you are able to see me, please type in clear, then we will start. This is not going to be a lengthy lecture. I think it is going to come out to be around 1 hour, 1.5 hours. That's it. It's going to be 1 hour, 1.5 hours. That's it. Because we are left with only Zener diode and logic gates. Hi Bunny, hi. So if you type in clear, yes, Bunny has said that it is clear. Okay, one small promotion kind of thing, guys. Already there is a crash course which has started, right? So the people are taking it seriously and they are learning a lot from the master teachers. If you are interested, you people can enroll into this crash course. Just keep that in mind. Okay, now let us go back. All of this has been done, and as I promised, all of this will be shared as a single PDF for you. All of this will be shared as a single PDF for you. You don't need to worry. All of this will be shared as a single PDF. Last class and today's class, so that entire semiconductors will be there in one single PDF for you. It's okay, Mr. JEE aspirant. It's fine, right? Learning is important. Okay, fine. What is a Zener diode? Man, a heavily doped PN junction diode can be used as a Zener diode. Look, what is it? Heavily doped PN junction diode. So what happens when the diode is going to be heavily doped, and how are they going to represent it in the circuital diagrams? How the Zener diode is going to be represented in the circuital diagrams? The Zener diode is going to be represented like this. Under the normal forward biasing, Zener diode behaves just like any other diode. Behaves just like any other diode. Okay. So under forward bias situation, how a normal PN junction diode is going to be behaving, heavily doped PN junction diode, which is called as Zener diode, is also going to behave in the same way. There is a speciality with Zener diode when it is operated in reverse bias. Zener diode is special when operated in reverse bias. When it is reverse biased, then it is special. That's why if you look at the graph, look, current versus the voltage. So barely you have any forward bias diagram drawn. Reason being, majority of the times, every time when we take a Zener diode, we operate it in reverse bias only. So that's why you can see complete graph for forward bias is not drawn. If you have to draw a complete graph for forward bias, it is just going to look like the normal diode, normal PN junction diode. How it is going to look like? It will look like the same thing here also. It will look like the same thing even in the case of Zener diode also. Okay, fine. And what is the speciality with reverse bias? Look, as the reverse bias voltage is increased at one particular voltage called VZ, called as Zener breakdown. At one particular voltage, all of a sudden there is lot of current flowing, but more or less the voltage is constant. At a particular reverse voltage is remaining constant, but current is increasing. Can you see that? Once you reach that voltage, all of a sudden it is allowing huge amount of current to flow through it, but the potential difference across it is not changing. That's the beauty. It is just like the breakdown, but the avalanche breakdown is different from the Zener breakdown. Avalanche breakdown is different from the Zener breakdown. So Zener breakdown is different. Zener breakdown is different from avalanche breakdown or avalanche breakdown. See, when avalanche breakdown is going to take place, what will happen? You'll have minority charge carriers. As you keep increasing the voltage in the reverse bias, as you keep increasing the voltage, electric field keeps increasing. As a result, the minority charge carriers will gain lot of kinetic energy, and they make collisions and make the electrons which are there in the bonds become free. So one goes and strike the electron in the bond. That electron also becomes free. Now you have two. Two will go and strike. Will become 4. 4 will become 8. As a result, the whole diode gets destroyed. But in the Zener breakdown, we will get lot of free charge carriers, but they are not as dangerous as avalanche breakdown. You won't find the proper explanation for Zener breakdown in the books also. Okay, so in Zener breakdown, we get lot of free electrons, but they don't have lot of kinetic energy to create avalanche breakdown. So if avalanche breakdown is going to be kicking in, then the whole diode gets destroyed. So how different is this Zener breakdown, and how much it takes to reach avalanche breakdown? Okay, look, we are going to have a heavily doped one, right? We are going to have a heavily doped PN junction diode. As a result, the depletion region is going to be thin, because you have lot of holes. As the holes are going to be stronger, many holes are going to be there rather than the normal PN junction diode, and many electrons on the inside when compared with the normal PN junction diode. So when the population of the majority charge carriers is too big, they will be crushing this depletion region or this barrier, because they desperately want to go to this side and that side. Holes want to go this side, electrons want to go this side. So they will be pressing. As a result, the depletion region is small, and whatever the electric field will be inside this depletion region, as this is going to be very small, this is going to be very strong. You know the potential difference, right? If the potential difference is kept constant, for example, if the potential difference is kept constant, but you are decreasing the distance, then you need to have more electric field to create the same amount of potential difference. The potential difference is going to be minus E bar dot dr bar. So if the distance is going to be decreased, automatically electric field will increase. Yes. When we apply reverse bias, there is potential difference, but as the thickness of the depletion region is very small, to create that potential difference in that very small amount of gap, electric field will be very strong. If the electric field is very strong, the electrons experience force due to this field. Electrons experience force due to this field, and the electrons can become free because of this electric field, and that type of emission is called as field emission. As E is very strong, electrons get free from bonds, electron gets free from the bonds due to the force applied by that electric field, and this is going to be called, field emission. This is called as field emission. Now you might have a doubt, sir, for how much amount of electric field can this field emission take place? Roughly for how much amount of electric field? So if the electric field is greater than 10 to the power 6 volt per meter, then this much amount of electric field is strong enough to break the bonds in which electrons are involved, and electrons are going to become free. Okay, fine. Now look, heavily doped will have strong electric field, but that electric field, whatever is there, is not enough to make the electrons free. Now, as I apply the reverse voltage, this strong electric field becomes even stronger. As the negative voltage across the PN junction diode or the Zener diode is increased, as the negative voltage increases, the potential difference across this barrier also keeps increasing. That means the electric field should become stronger and stronger. When the electric field is around 10 to the power 6 volt per meter, that's when the Zener breakdown happens and lot of holes and electrons are created. When you have lot of holes and electrons created, then what will happen? Automatically you will have lot of current flowing. That is what exactly happened at that voltage. So when there was no biasing, although there is strong electric field, that electric field was not enough to produce the free electrons. As I keep increasing the voltage onto the negative side, yes, the field inside the depletion region also is increasing. At this particular voltage, that field was able to emit the electrons. And that's when the voltage at which electron emission has taken place is called as Zener breakdown. Now, 1 second. Sir, what will happen if I further keep trying to increase the VZ? If you are trying to further increase the voltage also, the voltage across the Zener diode will remain to be the breakdown voltage only, but it keeps taking more and more amount of current. But there is a limit for everything. Look, once the breakdown happens, once the breakdown takes place, once Zener diode breaks down, it is observed that voltage across it is constant, but it is able to send different currents. For example, you only see here, once the breakdown has happened, it is able to send this much current through it. It is also able to send this much current through it. So for the same potential difference, once the Zener diode is going to break down, it can allow any amount of current, but there is a limit. Because too much of current also is going to be bad for the Zener diode. If too much of current is made to flow, too much heat gets generated. Too much heat getting generated is also going to be damaging the Zener diode, right? So there will be power rating for Zener diode also. There is power rating for Zener diode also. There is power rating for Zener diode. To make you understand, example, so the power rating of the Zener diode is 2 watt and the Zener breakdown voltage is 5 volt. If this information is given to you, then what they are trying to indicate, see, power is going to be V into I. So 2 watt, voltage 5, I. So what is the current? Current is going to be 0.4 amps. This is an indication that when the power rating is going to be given to the Zener diode, they are trying to give us some information. What is that information? That Zener diode can make or can accept or can allow up to 0.4 amps of current without getting damaged. So for safe operation of this diode, current through diode should be less than or equal to 0.4 amps. So this is the information you get from the power rating of the Zener diode. Right? You have a lot of questions on these kind of things. So what we realized is that once the Zener diode breaks down, the voltage across it will be constant. And it can take any amounts of currents, but there is a limit for that any amount of current also that will be known from the power rating of the Zener diode. If the maximum current the Zener diode can take is up to 1 ampere, So it can take up to 1 ampere. If the current that is going to go through it is going beyond 1 ampere, then the Zener diode also is going to get destroyed. Okay. Now, just a second, man. Just a second. How this Zener diode is going to be helpful for us, that I have to explain. I need one more slide. Just a second. Zener diode is what we call logical. Many people won't have proper understanding of it. So I have properly explained it. Now, how it is going to be used as a voltage regulator? How Zener diode can be used as voltage regulator. For example, I have a TV, man. Let us say I have TV. Take this to be television. And if the voltage across the television is going to go beyond, let's say, 100 volt, it gets destroyed. If voltage across TV goes beyond 100 volt, goes beyond 100 volt, it gets destroyed, or you can say it gets damaged. So at any cost during the power fluctuations also, the voltage across the TV should not go beyond 100. So what I will do is, I will connect a Zener diode in reverse bias across this TV, and the Zener breakdown for this one, I will keep it to be 100 volt. Then from the main supply, whenever huge currents are going to enter, if that entire current is going to go through the TV, if the potential difference across the TV has to go beyond 100, if the potential difference across this has to go beyond 100, the moment it reaches 100, Zener breakdown takes place. Then that extra current, whatever is supposed to flow through the TV, will be made to flow through the Zener diode, and the Zener diode will maintain 100 volt potential difference across this TV, and it will not allow the voltage to go beyond 100. It will not allow the voltage across the TV to go beyond 100. If this was not there, the total current should go through this one. It will have certain amount of resistance. So definitely the potential difference across this is going to be I into R. So if the I is big, I into R will be big. As a result, the voltage will be big. As a result, the voltage might go beyond 100. So the moment current is going like that, normally this is inactive. But when the current that is flowing through the TV is coming closer to 100, that's when the Zener breakdown takes place. So then once the Zener breakdown happens, it will maintain 100 volt potential difference across the TV at any cost. Now you might have it out, sir, what if some extra current is sent? How much ever is needed to be sent into the TV to maintain 100 volt potential difference, that much only will be allowed to go into this one. Rest all extra current will be taken by the Zener diode. Rest all will be taken care by the Zener diode. So in this way, Minu, hello man. In this way, we are safe. So using the Zener diode, we can safe keep all the appliances. But proper breakdown voltages have to be taken care of. So how questions are going to be coming on this? So the theory of Zener diode is completely done, man. Completely done. And whenever you see a graph where the forward bias graph is not completely drawn, that's a graph for Zener diode, right? So the IV characteristics of electronic device shown in the figure is this, right? And this is for sure a Zener diode which can be used as a voltage regulator. Hi, Manu, sorry. Okay, now look, this question is very good. This question is very good. See, whenever logic gates is going to come, na, you have to be literally a bit disappointed if you are writing uh, in your shift. In your shift, if logic gates question is going to come, you have to feel bit disappointed because logic gates is bit easier. Logic gates is bit easier. If Zener diode question is going to come, not everyone will be able to solve Zener diode question. Only those people who have good teachers would have explained Zener diode in a proper way, and they will definitely do good. They will definitely do good. So you should be thinking in this way that in my shift, Zener diode question should come such that I will be standing out when compared with the other people because majority won't be able to solve. That's how you have to think. Okay, fine. In the given circuit, if the power rating of the Zener diode is 10 milliwatt, they gave the power rating, man. If they are giving the power rating, that means they are indirectly telling you that you can't allow how much ever current you want to flow into the Zener diode, it can get destroyed. So you have to make sure you are going to send a current which is going to be less than the rated current. Okay, so now let us do this. Man, power is V into I. Power is how much? 10 into 10 to the power minus 3. How much is the breakdown voltage? 5. So, what is the current that you can send into the Zener diode? Maximum we can send 2 milliamps. So, I realized it. So, the maximum current that can be the maximum current that can be sent through the maximum current that can be sent through Zener diode is how much? Is 2 milliamps. So you can send in any current between 0 to 2 milliamps. If you are trying to go beyond 2 milliamps, yes, this Zener diode is going to be damaged. So safe operation won't happen. Okay, fine. Now the value of series resistance Rs to regulate the input unregulated supply is, man, they said this is 8. If the Zener diode is broken, like breakdown, the breakdown has happened. If the breakdown has happened, then the potential difference across this one will be how much? The potential difference across these 2 points will be maintained as 5 volt. Then let us take the current through this one to be IL. Current through that to be IL. Now you tell me 5 volt is going to be, resistance is 10 to the power 3 into IL. So what is the current that is always flowing through this load resistance? 5 milliamps. Why? Once the Zener breakdown takes place, it will maintain the voltage to be 5. Then if it is maintaining 5, always the current through this should be 5 milliamp. And how much current is going to go through the Zener diode? That you write it as Ig. Let us take this current to be I. So if we use common sense, I is going to be what? Ig plus I load. Now, what can be the maximum current? Man, IL is fixed, man. IL is fixed. You can't do anything to that. Because once this is going to be broken, or once the breakdown happens, voltage will be 5. So it is always 5 milliamp. But current through the Zener diode can change from 0 to maximum 2 milliamp. So if you want the maximum current supply, then obviously there should be maximum current flowing through the Zener, and anyway this is always 5 milliamp. So the maximum current that can flow is 7 milliamp. Okay. Now, if you are going to talk about the minimum current that is going to flow when the Zener breakdown happened, obviously Iz plus IL, so this can take up to 0. then the minimum current that is going to be coming from the supply can be 5 milliamp. Now look, when the Zener breakdown has happened, if the voltage across this is 5, total has to be 8, voltage across this should be how much? 3 volt or not? Right? So I into Rs is going to be 3 volt. So Rs is going to be 3 by I. So Rs minimum, if I am going to talk about Rs minimum, then I am talking about what? 3 by I, where I has to be maximum. So how much? 3 by 7, man. 3 by 7 kilo ohms. Why? 7 milliamps. Na? If it is going to go up, it will become kilo. Minu, you can expect one question from semiconductors for sure. So yesterday's class, today's class put together, you can expect one question. But today's class alone has the probability of 80% to be there in the examination. Zener diode and logic gates put together, 80% of the times questions will come from only these two. And in the rest 20% of the times, you will have theoretical questions from the previous class and some numerical questions from that NE into NH is equal to NI square, that's it. Okay, fine. Now if I want, see, I into Rs should be 3 volt. So if I want my Rs to be maximum, what can be the maximum value of Rs? It is going to be 3 into I minimum. So what is the minimum current? 5. So 3 by 5 kilo ohms. So maximum is 3 by 5, minimum is 3 by 7. Which option? This option. It's a very good question. And when this question has been asked, majority of the students were not able to answer it. Majority were not able to answer it. They were not able to think this clearly. They should have the conceptual understanding before the examination. In the examination, they won't be able to think of it, right? Okay, fine. And one more thing. Sometimes they won't ask the range of Rs. Sometimes they won't ask the range of Rs. Sometimes range of Rs value won't be asked. They simply say find Rs. Then indirectly they mean Rs maximum. So if they simply say find Rs, you find the Rs max. If they simply say Rs, you find Rs max. Okay, I'm not going to leave. I have taken up all the questions. Even 2023 questions also I have taken for better conceptual understanding of you. Kanupasami, no man. If you are in 11th, then don't watch it. If you are in 11th, don't watch it. This is semiconductors, which is a 12th topic. If you have watched the previous class, then you can watch this one. Anyway, it is an independent concept. Semiconductors is an independent concept. If you have watched the previous class, now you can watch this class. If not, you better leave it. If you are in 11th, you better leave it. Okay. A Zener diode of power rating. Come on. Again, power rating is given. So as the power rating is given, and what is the breakdown voltage of Zener diode? 8. So the power rating is going to be V into I, which is going to be 1.6. Voltage is 8 into I. So what will be the I value? It is going to be 0.2 amps. That means the maximum current that can flow through the Zener diode is 0.2. If you are trying to make a current more than 0.2 to pass through the Zener diode, not safe. Okay. it has to regulate the voltage fluctuating between 3 to 10. Okay. The value of resistance Rs for safe operation of the diode. Man, if the diode is in the breakdown situation, that's when current will pass through it. If the diode is in breakdown situation, the voltage across it will be 8, and the maximum you can have about this is 10, then the maximum voltage you can have across this is 2 volt. Right? So, what is the maximum current that you can send across this one? It is going to be 0.2 amps. So, the maximum current flowing through the supply should be 0.2. Okay. In that situation, what is that? V is 2 into I into R, right? I is 0.2 into R. So Rs. The value of Rs is 2 by 0.2, which will turn out to be what? 10 ohms. So I'll mark this. I'll mark this. Right? The maximum current I can send through this one is 0.2. If there is a supply of 0.2 in this one, then fine. When 2 volt is there. When this is in the breakdown situation, and if the when it is in the breakdown situation, voltage across this is 8, and voltage across this one is 2, right? So if the resistance is going to be less than 10, for example, if the resistance, for example, okay, I'll write this side. For example, if Rs is going to be 5 ohms, if the Rs value is going to be 5 ohms, then 2 volt is going to be I into 5, then the current is going to be how much? 0.4 amps. So if there is 0.4 amps flowing, that 0.4 should go through the Zener diode, which is not safe. So the resistance should not be less than 10 ohms. Resistance should not be less than 10 ohms. Here I have to put minimum minimum. So if you ask me, this question is a weird one, man. If you are going to keep it 12, 13.3, 13 also, it's going to be safe. That's why I hate JEE mains. Okay, do this question. See, no power rating. So we don't need to worry. No power rating. But we have to see whether the Zener diode will break down or not. If the Zener diode is not breaking down, then no current will flow through the Zener diode. You can say that the Zener diode is an open circuit kind of thing. So Zener diode won't contribute for the circuit. Sir, how do we know that the Zener diode is in the breakdown situation or not? First of all, forget that this is existing. If this is not present, just take like that. If this is not present, then what should be the voltage across 500? Let us say you take some I, and that I is going to be 20 divided by 700. And now potential drop across 500 ohms is going to be 500 into 2 by 70. 0 gets cancelled out. So it is going to be 100 by 7, which is more than 10 volt. So if this Zener diode is not in the breakdown situation, the voltage across this 500 ohms should be more than 10. But will the Zener diode agree for that? No. That's a clear indication that this is in the breakdown situation. If it is going to be broken down, then it's a clear indication that the voltage across this will be maintained as 10. Then what is the voltage in this one? Voltage across this will also be what, 10, because this one and this one are in parallel. So the current in this, I'll take it as some I1. Then the I1 is going to be what? 10 by 500, which is going to be 1 by 50 amps. If across this one there is 10 volt, then across this one, how many volts? Obviously 10 volts, because total should be 20. Then what is the current flowing through this one? 10 divided by 200, which is 1 by 20. Then how much current is going to go through the Zener diode? The current that is going to go through the Zener diode is going to be I minus I1, which is going to be 1 by 20 minus 1 by 50, which will come out to be how much? 30 divided by 1000. So you can say 30 milliamps is going to go through the Zener diode. So first of all, be careful when these questions are going to be given. First, you have to see whether the Zener diode has come to a situation where it has reached the breakdown situation or not. Right? If the Zener diode is not achieved the breakdown, then it is just like any other diode. No current flows through that diode if it is in reverse bias. So how to identify whether it is going to be broken down or not? As I said, you forget about the diode and you just calculate the potential difference across which it is connected. If the potential difference is coming more than the breakdown voltage, then the Zener diode will break down. If the potential difference is coming less than the rated voltage of the Zener diode, then the Zener diode won't break down. If it is not going to break down, it won't allow any current, or you can say negligible current is allowed to flow into it. So a very important thing, please write it down. What is it? If Zener diode doesn't break down, it doesn't allow any current through it. So it's very important for us to check whether it breaks down or not. Whether it breaks down or not. It's very important for us to check. How do we check it? I already gave you how to check it. Forget about the diode, you just take the normal circuit. In the normal circuit, if the potential difference across the resistance is coming out to be more than the breakdown voltage of the Zener diode, that's when the Zener diode is active, otherwise it is inactive. That's it. Okay. All those people who love the content, whatever is being delivered over here, please press the like button. Please press the like button. Okay, one more question. 2024 wala. In the given circuit, the breakdown voltage of the Zener diode is 3 volt. I don't know whether the Zener diode is going to be in the breakdown situation or not. Forget about this then. Forget about that Zener diode. I want to check whether the Zener diode will be broken down or not. For some time, forget about it. You think that it doesn't exist. This one doesn't exist. Think in that way. Then, whatever the current is going to be flowing, that current goes through this. So that current, I'll simply write it as V by the total resistance, which is going to be 10 by 3 kilo ohm, which will be milliamp. Now the potential difference across the 2 kilo ohm one is going to be I into R, which is going to be 10 by 3 into 2, which is going to be how much? 20 by 3. 20 by 3 is definitely more than 3 volt. That's a clear indication that the voltage, if the Zener diode is not going to be there, then the voltage across the 2 kilo ohm will go more than 3. If I put the Zener diode, it won't allow it to go more than 3. That means definitely this Zener diode is in the breakdown situation. If it is in the breakdown situation, what will be the voltage across this? 3 volt. Then what will be the current that is going to be flowing into this? I'll take it to be I1. It's going to be voltage 3 volt divided by 2 kilo ohm, which is going to be 3 by 2 milliamps. Okay. Fine. If this is going to be 3 volt, then this is going to be 7 volt. Then the current that is flowing in this is going to be 7 by 1 kilo ohm, which is going to be 7 milliamps. I can see that 7 milliamps is coming over here. 7 milliamps is coming over here and 3 by 2 going into this. Then how much will go into the Zener diode? Obviously, the current through the Zener diode is going to be what? The total current which is entering, which is 7, minus the current which goes into this branch, which is 3 by 2, which is going to be how much? 11 by 2 milliamps, which is going to be how much? 5.5 milliamps. I don't know whether you have noticed it or not. This question, this question, this question, this question. Okay. All the 4 questions, more or less, I have done the same approach. Super Rishi, super Mr. Rishi. Okay. Now let us go to the logic gates. We are done with Zener diode. All the possibilities, theoretical part has been covered, numerical part has been covered. There is nothing left. There is nothing left in Zener diode. Now let us go to the logic gates. So before I go for the logic gates, how the inputs are going to be? See, high will be taken as 1, low will be taken as 0. Always keep that in mind. High will be represented with 1. Low will be represented with 0. Sometimes on will be represented with 1. Off will be represented with 0. So, in these logic gates, we have different types of gates. We will talk about all those different types of gates, right? And I will talk about analogous. I will draw some analogy also for you to better understand. So we are going to have, let's say, something called as AND gate. So how an AND gate is going to be represented in the circuital diagrams? Vertical line and a symbol like this, then. So here we write A and B, and here we write Y. A comma B are the inputs, Y is the output. So how to feel this AND gate? How to feel this AND gate? Look, for example, I'm drawing some analogy with this circuital thingy. When the bulb will be on, if you just close one switch, will the bulb be on? No. This switch should be closed, or this switch should be closed. Both the switches have to be closed, only then the bulb is going to glow. That means both the switches have to be on. Okay. Now there is something called as truth table. Let me just go back to the diodes and let me just talk about something called as truth table. A, B, output is Y. So how you have to analyze is that if the bulb is on, output is high, or you can say output is on. That's how you have to check. Okay. Now, if A is on, A will be represented. On means 1. That means you close this. But you have kept this open. Will the bulb glow? No. Bulb will be off only. A is on. B is also on. If both of them are on, then current will flow, bulb will glow. Bulb will be on. A is off. That means A is open. But B you have closed. Will the bulb glow? No. A is off. B is also off. Will the bulb glow? No. Bulb will also be off. So if you are going to look at this table, can you see that, and can you say that it is some A into B, A 1 into 0, 0, 1 into 1, 1, 0 into 1, 0, 0 into 0, 0. So that multiplication thingy is working out over here or not? So that's why the output of Y will be written as A into B. Y is A into B, that's the AND gate. That's the AND gate. Okay. Now let us talk about OR gate. Let us talk about the OR gate. So how the OR gate will be represented? You will have two inputs, but the wire, or you can say, so not wire, but the line will not be a vertical one. Here you can see in AND gate we have a vertical line, and in OR gate we are going to have a bent line. That's how you identify the difference between OR gate and AND gate, which is important. So I'll draw some analogy of this OR gate to current electricity. For example, we have one switch like this and we have one more switch like this. You can take this as switch A, this as switch B, and we have the bulb and we have the battery. If I close A, then yes, there is a way for the current to go through A and pass through B, then the bulb will be on. So how the truth table is going to look like? How the truth table is going to look like? Input A, input B, output Y. So if A is on, but B is off, off means switch is open. So if A is on, the current will flow through A and will flow through the bulb. That means bulb will be on. So 1, 0, 1, 1, 1. Man, you have closed A, you have closed B. That means A is on, B is on. Then current will flow. That means bulb will be on. On means 1. Next, let's open A, close B, open A, close B. Still the current will flow through the bulb, bulb will be on. If you keep both of them open, then the bulb will not go, because there is no way that the current is going to flow through the bulb. What doubt? Santi. Hi Sanjay. Sanjay, where are you from? Mr. Sanjay. Okay. Meanwhile, 1 plus 0, 1. 1 plus 1, actually it should be 2, but on will be on. Okay, that you take an exception. 0 plus 1, 1. 0 plus 0, 0. So that's why the output will be represented with A plus B. Will be represented with A plus B. Santi, you can ask. Santi Murugesan, you can ask. Null. Okay, fine. Now look, there will be something called as NOT gate. NOT gate. There will be something called as NOT gate. So how the NOT gate will be represented? This is how it is represented. You will have single input, single output. Okay, Sanjay. Single input, single output. So how to feel this NOT gate? For example, you have a bulb, and across the bulb you have connected a conducting wire, but you have kept a switch. Now, if you look at, if the switch is closed, then the current will flow through the conducting wire, will not flow through the bulb. So if the switch is on, then the bulb will not glow. If the switch is open, then the current will flow through the bulb and the bulb will glow. So exact reverse. So the truth table for this is so simple. Input A, output Y. If the switch is on, then current will go through the switch but not through the bulb. Bulb will be off. If the switch is open, then the bulb will be on. So the output is going to be written as A bar. When you see bar, that's an indication. That's an indication that you have to talk about opposite. High opposite is low. Student of Kiran sir, I will be doing fluid mechanics, don't worry. I will be doing fluid mechanics, don't worry. Okay, fine. Now look. What if AND gate is connected to NOT gate? Then we call it as NAND gate. And we call it as NAND gate. We have A, B. What is the output that is going to come from here? A into B. After passing through the NOT gate, A into B bar. So the output is going to be AB bar. Output is going to be AB bar. Okay, fine. Then there is one more representation. They won't represent like this. Whenever you come across NAND gate, the representation will be slightly different. There will be a knob kind of thing drawn on the AND gate. Whenever you see that knob, that's a clear indication that we are dealing with NAND gate. So what will be the truth table, man? The output is going to be A into B bar. That means when you do A into B, whatever you get, you have to mark the reverse of it. Okay. Now, let us talk about the truth table for that. Let us talk about the truth table for that. So the truth table for that is going to be A, B, Y is going to be what? A, B bar. A1, 0. So 1 into 0 will be what? 0. So 0 bar will be what? 1. 1 into 1 will be 1. 1 bar will be what? 0. 0 into 1, 0. 0 bar will be what? 1. 0 into 0, 0 bar will be what? 1. Okay. Now, same way, we have NOR gate. We have NOR gate. Same man, same story. You have to just put one knob indicating that for OR gate we have connected NOT. A, B, Y, A plus B bar. So what will be the truth table? What will be the truth table? We have A, we have B, Y is going to be A plus B bar. A, 1, 0. 1 plus 0 will be what? 1. And 1 bar will be what? 0. 1, 1. 1 plus 1. We say 2, but my intention over here is going to be on off thingy, right? So 1 plus 1, which is going to be written, normal math is 2, but it's still we write it as on. On means 1. So 1 bar will be what? 0. 0, 1, again on, 1 bar, 0. 0 plus 0, which is 0, which is going to turn out to be what? 1. Now I'll give you one more extra thing called as XOR gate. Sometimes they have asked, so you need to have a rough idea about it. XOR gate. So how the XOR gate will be represented? You will see a symbol like this. One more extra additional line will be there. This is your inputs and this is your output, which is A into B bar plus A bar into B. So what will be the truth table for this? What is the truth table for this one? A, B, Y is going to be A B bar plus A bar into B. This sometimes will be referred to as this. Both of them are same. Representation is just different. Okay, now A1, B0. Now you only do the A1, B bar, that means 0 bar, 1. So 1 into 1, 1. So I'm not bothered about what will be over here. If this is 1, for sure the total should be 1. 1, 1. Then what will happen? 1. 1 bar, 0. So 1 into 0. Next, 1 bar, 0. 0 into 1, 0. 0, 1. So if I'm going to put A as 0, 0. 1 bar is again 0. 0 into 0, 0. Now let us talk about A bar. A bar, 0 bar, 1. So 1 into 1, 1. Next, let us talk about 0, 0. 0 into 0 bar, which is 1. So 0 into 1, 0. Next 0 bar, 1. 1 into 0, 0. So if you see 2 ones and 2 zeros in the truth table, in the output, then we are talking about XOR gate. Yes, Sanjay, true. Next. Sometimes they are not going to give ones and zeros, they are going to give a graph. Sometimes 1 zeros won't be given, but graphical representation will be given. Graphical representation for inputs will be given. For example, they'll give a graph. How? Look at this. They give a high, then like this, then like this, again they give like this. Whenever you see highs, this is an indication of on. That's an indication of on. This is a low. This is going to be off. Off in the sense 0. Or you can also write it as low. This is a low value. And this is a high value. So you are going to count it as 1. So this will be taken as 0. This will be taken as 1. So you just need to know when they are going to give graphs like this, you need to identify what is the input. You need to identify how the input is going to look like. How the input is going to look like. With this, we are done with the basic theory. Now, we are into questions. We are done with the basic theory, we are into questions. So the truth table for this given circuit is, lot of things have been given, man. Lot of things have been given. Come on. For example, and one more thing, man, don't randomly start the question. When options are given, if you do which case, will we get a unique answer? You look 0, 0, 0, 0, 0. Here 0, 0, 0, 1. So if I do first case, if I check the first one, that is 0, 0 input wala, then 2 options get eliminated. I'm not happy. Let me check whether I can eliminate 3 options. 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1. No, man. I can eliminate only 2 options at once. So for that, what I'll do is, I'll go for 0. If I go for 0, that 0 is shared, 0. But that 0 goes, as it is a NOT gate, will become 1 here. Right? Next, B, 0. 0 goes here. Now the same thing is connected to this one also. Then as it is an AND gate, 0 into 0 will give an output of 0. 0 into 1 will give an output of 0. Then what is fed? 0 and 0 are fed, and it is an OR gate. So 0 plus 0 will be 0. So when you are going to send 0, 0, output is 0. That means these two are ruled out. Your answer should be between first option and second option. Your answer should be between first option and second option. Okay, now if I am going to be verifying the second one, then the second one is different for both of them. So I will verify for the second one. I will verify for the second one. So I will use different color. Second one, A is 0. If A is 0, it is 0. If A is 0, it is 0. But that 0 will become 1 here. Okay. Now, if I am going to talk about this one, this is 1. 1 is sent. All the circled ones are the second parts. So 1. So here what will happen? 0 into 1 will become 0. And 1 into 1 will become 1. And then 0 goes to OR gate, 1 is going to go to the OR gate, 0 plus 1 will be what? 1. So what are you going to get? You are going to get this. So which option? This option. It's this option. That's how you have to do. Yes, Chahat Kumar, you're correct. Do this. Logic operations performed by the given digital circuit is equivalent to which gate? So for that we need the truth table, right? For that we need the truth table, right? Okay. Now let us look. Let us send 1. So 1 and the very same 1 will go to this one, right? And let us send 1 into this. Then the very same 1 will go here. The very same 1 will go here. As it is OR gate, 1 will come out. As this AND gate, 1 will come out. And that 1 will be fed to NAND gate. 1 will be fed to NAND gate. So 1 into 1 should be 1, but as it is going to be NAND gate, output will be 0, which is going to turn out to be what? 1. So when you send 1, 1, output is 1. So OR is ruled out. Oh, not OR. Very bad, man. NOR is ruled out. Why? 1 plus 1. 1 plus 1 will give you 1. That means OR gate will be there, and 1 into 1 will be 1. So AND gate also possible, but not NAND gate. So now your answer lies between AND and OR. So now I will choose a different input. I will choose 0 and here I will choose 1. Then 0 goes to this, 1 goes to this, the same 0 goes to this one, and the same 1 goes to this one. Now 0 plus 1 will be 1. Okay, I will circle them such that you will understand that we are doing the second thing. Now 1 into 0 will be 0. So 1 and 0 will be fed to this NAND gate. 1 into 0 will be 0. But as it is NAND gate, it will become 1. And then after crossing through the NOT gate, output will be 0. Now look. Input are what? 0 and 1. So if it is OR gate, 0 plus 1 should come out to be what? 1. But output is what? 0. It is just like AND gate. It is just like AND gate. Okay, fine. Next. Do this. 2023 11th April morning shift. I have taken 2024 also, don't worry. Okay. The logic performed by the circuit shown in the figure is equivalent to. again NAND and OR NOR. Okay, I'll send 1 that gets split into 2 wires, so 1 1 OR gate, NOR gate 1 plus 1 1 and 1 bar 0. I'll send 1 1 1 again this 0, same na, up and down is same. So 0 0 goes over here again, or 0 plus 0 is going to be what, 0, but NOT gate is there, so output will be 1. So if you send 1 1, output is 1. So NAND is ruled out, NOR is ruled out. Now we have to check between AND and OR. Okay, now look, I will send 0 into this, then 0, then 0. So 0 plus 0 should be 0, but as it is NOR gate, you will get 1 out. Now if I send 1 into this, then 1, then 1, this will be 0. Now you are feeding 1 and 0. 1 plus 0 should be 1, but as it is 1 plus 0 should be 1, but as it is NOR gate, opposite, reverse it. So 0 1 if you send, output should be 0. If it is an OR gate, 0 plus 1 should come out to be 1, but we got 0 and 1 to be 0, that means it is AND gate. OR gate is ruled out. Array, these are the questions that are coming, man. What can we do? Whatever the questions are there, those only I have picked. Okay. That's why logic gates is a very easy topic. Logic gates is very easy and very scoring. And majority of this... it's okay, Sanjay. Following gate section is connected in a complete suitable circuit. For which of the following combination bulb will glow? Only thing which you have to keep in mind is that bulb will glow when there is potential difference across it. That means if this is going to be high, then this should be low. Or if this is going to be low, then this should be high. Then only you will have difference. Then only it will glow. So either here 1 0 should come or 0 1 should come, only then the bulb will glow. 1 0 or 0 1 should come. Either we should get 1 comma 0 or 0 comma 1. Keep that in mind. So when are we going to get that? You only check the options. Okay, I'll try to directly go without wasting your time. I don't want to waste your time. I'll check option B, man. I'll check option B. When I check for option B, let us take it here. A is 1, right? So 1, 1 as it is NOR gate, 1 plus 1 should be 1, but as it is NOR, 0. What about B? B is 0. What about C? C is also 0, and it is 0 into 0 is going to be 0, but it is NAND gate, it will become 1. So 0 will go here, 1 will go here. Now what will happen? 0 plus 1. 0 plus 1 should be 1. 1 and it is NOR gate, so it should become 0. Okay, fine. Now let us look at D. D is given as 0. So 0, 0. NOR gate. So 0 plus 0 will be what? 0. And 0 bar. Or you can say not NOR gate, right? So it is going to be 1. Yes. What happened? I got a low on the left side and I got a high on the right side of the bulb. So bulb will glow. So answer should be B. Okay. Now for simplicity, what I'll do is, like for better conceptual clarity, I will do one more option. Let me just do D option. So let us put it over here. D option. A 0. If A is 0, 0 will be fed 0 will be fed. So 0 plus 0 should be 0, but NOR you will get 1. Now here you are getting 1. Now let us look at B. B is 1, C is 1. Circled ones are second things. So 1 into 1 should be 1, but it is NAND gate, it should be 0. So 0 is fed. So 1 plus 0 will be 1, and as it is NOR, so the output over here is 0. Next D is 1. So 1, 1. 1 plus 1, 1, and NOR gate, right? So I have to take it to be 0. So here we'll have 0. What happened? Low. On other side also you have a low value. There is no potential difference, so the bulb will not glow. So that means this option is wrong. So like that you have to check for all the options. So basically this question is going to be consuming time. And second thing is that as they are asking whether the bulb is going to glow or not, people should realize that 1 and 0 should come, or 0 or 1 should come. 1 0 or 0 1 should come. That people should realize in the examination. Okay. Look at this. See, this is question. These are the options. This is one option. One second. This is one option. Option A. Right. This is one option. You can take it as option B. This is going to be option C. This is going to be option D. This is option D. And this one is option C. Man, be smart. Don't randomly start. Look at the graphs where the difference is there. Based on that, you eliminate the options. Based on that, you eliminate the options. Okay. Look, if I look at A and C, the second part itself are different for A and C. So if I am able to find for the second part, then I can eliminate one of the options. But I don't want like that. I don't want like that. I want to see in the graph, in all the 4, I want to see a unique one. Or at least I should be able to eliminate 2 options. At least I should be able to eliminate 2 options. Just to save time. Okay. Now look. Look at this part. Look at this part. Down, low. Last but one. Low. And these 2 options, high. Highs are formed. So if I check last but one, then I will be able to eliminate 2 options. So last but one. So the last but one, and it is a NAND gate. If you see over here, low and low, that means 0 and 0. So 0 into 0 bar will be what? 1. So that means a high should be formed. That means this is kicked out, this is kicked out. These 2 are wrong. Now I have to choose between B and C. Let us check where there is a difference. Man, if you are going to look at the last one, this is a low and this is a high. In B and C, this is a low, this is a high. So let us go for the last one. It's low and this is what? High. So 0 into 1 bar, which is going to be 0 bar, which is going to be 1. So it should be high. Then which option you are going to mark? You are going to mark this. You are going to mark this. Chahat Kumar Super. Okay. Next. This. Okay, again, don't try to draw the whole diagram. Eliminate the options. At least you should be able to eliminate 2 of them. And if you look at If you look at the very beginning part itself, high, high, low, low. So I can eliminate two options by knowing the first thing. So 0, 0. Both A and B's are 0. So 0, 0. Man, it is NAND gate. So 0 into 0 will be 1. Sorry. 0 into 0 will be 0. As it is NAND gate, it will become 1. This will become 1. So now 1 and 1 are fed. 1 into 1 will be 1. And this is going to be what? 0. So if you feed 0, 0, that is your beginning answer output should be 0. That means it should be a low. That means this is ruled out. This is ruled out. Now we have answer between B and C. I'll just go for the second part. Here it is a high. Here it is a low. Let me just check that. Look here. A is going to be what? A is going to be 0. B is going to be 1. So A will be 0. So this will come out to be 1. This will come out to be 1. But this is what? 1. So this will come out to be 0. 1 into 1, 1 bar 0. So 0 bar. So 1 into 0 should be 0. And as it is a NAND gate, it should be 1. So I should get a high. So here I have a low. So which option you are going to mark? You are going to mark option B. You are going to mark option B. Okay. Yes. We are done. With this, whatever is there in semiconductors has been completely done. Previous class and today's class. But today's class is more important than the previous class because majority of the times you will have questions on Zener diode or on logic gates. Theoretical questions, lot of theoretical questions are covered in the previous class. With this, we are done. Bye. All the best. Keep working hard. Vanakkam, Sita. Vanakkam. Vanakkam. And one more thing, if you want to ask something, you can ask. As we have completed a bit early, if you have anything to ask, you can ask. Or we will end the session. Yes, we have Sanjay. Sita, we have Sanjay. But we have Sanjay, who is a Tamilian. And we have many other people. Okay, fine then. I don't think you have anything to ask me. Bye. Good night. Keep working hard. You have very less amount of time.